Let us now discuss the heterogeneous versions of the GNNs, of the message passing GNNs, okay? And why directions are relevant. So far, we basically ignore the directions, or we assume that the graph is undirected, okay? We did so when we defined this bag of values of the previous layer by saying, okay, just collect the messages or the values of the neighbors of you, regardless of whether these are true incoming or outgoing edges. Then we aggregated and then applied the update function. Okay. What do we do when G is directed? How do we account for the fact that it is directed? So one approach, and so this is basically some taxonomy that is in this Rossi et al. Paper where they studied these three or the several options. Okay, three options. Um, One a model, the MPNNU model, basically says forget about the directions. They're all neighbors. Treat them on a par with each other. Okay, so we continue doing what we've been doing so far. The opposite approach is MPNND, which says, okay, we have directions of the edges. We let the messages flow in these directions. Okay, not the opposite direction. So we fully follow the directions of the edges. And here we will collect messages only from the incoming edges, not from the outgoing edges. Okay, and then there's the third option, which is Dear GNN or directed GNN, where we're basically saying, well, we're going to use both directions, but we are going to treat them in different ways. We are basically going to have two of these aggregated messages, one from the incoming edges and one from the outgoing edges. Okay, so here's an illustration of the three options. MPN and U, basically we collect these messages, and for regardless of one is an incoming edge, one is an outgoing edge, we simply ignore these directions. Here we say, okay, we collect messages only from the incoming edges. We ignore basically this edge. Well, once we'll consider this node will use this incoming edge, this edge that is incoming to the blue node. And Dear GNN basically says we're going to incorporate all of the edges. We're going to aggregate everything, but we are going to treat these in one way. So you see, this is one type of edges, and we're going to use this one in another way. So you see, there's another a different type of edge for the outgoing edges. Okay, a different type of an arrow. Okay, so basically these are the three options. Now, I will claim that the most informative, most flexible way is the Dear GNN approach. Okay, and why is it so? So remember what we do in GNNs. We basically collect information from neighbors in order to build a function that eventually will allow us to make a good prediction and generalize, our training data. Okay, and then express some interesting connections and patterns and so on. Now, on the other hand, edge directions come from a different world, different motivation. They express some intrinsic semantic of the connection in our data, like A follows B, or A is followed by B, or A sent a message to C. Okay, so there is some importance for these directions. Okay, so unlike the MPNND approach, we do want to account for edges of both directions. Okay, we do not want to ignore edges because of their direction. Okay, there's no reason to believe that the MPNN should benefit by ignoring one of these directions. However, unlike MPNN U, we do want to account for the direction itself. Okay, the follows semantics is different from the followed by semantics, right? Because this intrinsic semantic is of importance to the application. It does bear some importance. So this is something that we do want to take into account when we're building our model. Okay. So DirGNN seems like the way to go. How do we do it effectively? So we're basically going to build two bags. Okay. One bag looks at the outgoing neighbors of you, okay? And it is going to build one type of a message from each, and that's the first bag. The second one is going to look at the other direction and build, use possibly a different message function of for each of these, okay, for each of these nodes, and create another bag. So now we have two bags, B outgoing and B incoming. Okay, we distinguish between them with these arrows. Okay, so then our function, our update function looks like this. This is update k of HUK minus 1, comma, alpha k, but now alpha k is going to be an aggregation of two bags. And it's just a function that takes two bags, left bag, right bag, and produce one vector out of that. Okay? And in the next part, you're going to look at labels. And then we're going to extend this approach to include both directions and labels. Okay? And this is going to be defined in this section. Okay? So labels, where do they come from? Well, we know where they come from. If you have a relational database, then we know how to transform a relational database into a graph. Basically, the labels represent the relations from which the nodes are taken. Remember that each node corresponds to a row of the table. So this is a figure from the Rail Bench paper. So we have, okay, I remind you the way we produce the database. We have our tables with the foreign keys. This is a schema, basically. Okay, we have the database that corresponds to the schema. We have the rows connected with the foreign keys. We construct a node from every tuple, from every record of the database, connect them through these foreign keys. Here we don't see the directions of the edges, but you can imagine that the directions are there. It's because in this direction, in this figure, it's rather clear what the direction is, because all of the edges are between two different tables. But if you had like a follows relation between the person table and itself, then you would need this direction. Okay, so now we have this graph, and on top of that, we're going to define a graph neural network, like we did so far. Okay, so I remind you what heterograph is and what is a heteroschema. Heterograph or heteroschema or heterograph schema is consists of the node labels, edge labels, this mapping of edges or edge labels to pairs of node labels, and delta, which gives us the dimensions. Okay, and a heterograph over the schema basically follows the rules. It uses the corresponding labels, okay, and every edge labeled tau satisfies what M says. Okay, so M of tau should be the label of U, comma, the label of V if the edge connects U to V. Okay, and the dimensions follow delta, and that's all basically. Okay, so one thing that is really an important principle is that when you train GNN or an MPNN or a hetero MPNN, we really assume the schema. Okay, we really assume that the schema that we are using for the training set, validation set, test set, what we're going to use the GNN in the end follows the same schema. Okay, so everything should be consistent with the schema. Okay, when we talk about foundation models, they can actually generalize, or they're designed to generalize beyond the schemas. But pure GNNs are designed for a specific underlying schema. Okay. And again, the important cases, the important use cases are relational databases. You can also think of knowledge graphs very similarly. Okay. So first, we want to use a convenient notation. Okay, we want basically the labels to incorporate both the original labels and the directions. So we're going to do that. So we have an edge label tau, okay, where m of tau, tau basically connects a row 1 node to a row 2 node. Okay, tau edges connect row 1 nodes to row 2 nodes. That's the semantics of that. Okay, so we will say that tau is an outgoing edge label of row 1. Okay, leaves row 1, and an incoming edge label of row 2, of row 2, yes. Okay. Now, if you have a node U with the label row 1, then we will denote by n with this arrow outgoing tau, the set of outgoing neighbors of U through tau labeled edges. And in the, similarly, the set of incoming neighbors of U via tau labeled edges with this arrow getting into the n symbol. Okay? Now, this is the important notation. We're going to use this L double arrow, okay, double arrow E. This is the label set, the edge label set, okay, with this double arrow notation, which is going to basically incorporate these arrows. It is the arrow tau for all the edge labels tau, and arrow in the other direction tau. Okay, incoming tau for all edge labels tau. Okay, and with that, if you have a label, and we're going to denote labels of L double direction or double arrow with this tau prime. Okay, so one thing that we're going to do is to say, okay, we define here the incoming neighbors of U through tau edges and the outgoing neighbors of U through tau edges. Whenever it is not defined, for example, you are looking for the n of some irrelevant tau for a node U, then we will agree that this is basically an empty set. Okay, U does not have any neighbors and tau prime. Okay, so whenever it is defined, this is fine. If it is not defined, we simply will assume that we extend basically the definition to say that it is the empty set. Okay, so to define network MPNNs, we are going to use this enriched label set L double arrow rather than the original edge label set LE. Okay, that's the role of this notation. Okay, so how does the hetero MPN message function looks like? Okay, so basically we are going to build a bag for each label, edge label, tau, and each direction, whether it's outgoing or incoming. Okay, by simply aggregating the neighbors with the corresponding direction and edge labels. Very simply, okay? We can simplify this notation by using this double arrow L. Okay, so if you have tau prime in this L double arrow E, then basically we define a bag for each tau prime for this tau prime by following the tau prime edges. Okay, so this is simply the bag that follows the tau prime. Okay. Now, in a sense, if you think of what we're doing here, we are basically saying, well, we can use the MPNN-D model by looking at only one direction of the edges because we are going to reverse um, edge labels and have for each edge label the reverse edge label, and for each original label the reverse so for each original edge the reverse edge, with a notation of whether it is the edge in one direction or the edge in the other direction. This is basically what we're doing here. Okay, so how does it look like? Well, basically we just follow what we did with the directed MPNNs. Now we have our aggregation function, which is this is aggregation function at level k, okay, at round k. It is specialized to the label of U. Okay, so you can have different alphas for different node labels of U. So alpha of lambda of U takes as input basically all of the bags, for all of the um, tau prime, the directed edge labels in L double arrow E. Okay, so it basically takes as input a sequence of bags for every label and direction, and again aggregates all of them into one vector. And other than that, everything is just the same. We add it to to our original or the value of the previous round and apply our update function. Okay, so now yes, I said that this is a single vector, basically aggregates everything into a single vector. What you should notice is that if you have two nodes, U1 and U2, and they have the same label, then basically we define this update function, okay, well, how you update HUK in the same way. They have the same functions using the same parameters and everything. And that's important. Okay, we update nodes with the same label using the same function. Of course, they have different neighbors, so they won't necessarily get the same kind of the same update, but it is the same function that is defined for them. Whereas if you have different labels, they may have different alphas, okay, and different use each with each parameters.